Mhm.
So, okay, just let me say that this is our first preliminary webinar to the Congress, and yeah, and our lecturer is Jerry Stone, and yeah, Maria is your floor to introduce him and what we will be doing here today.
Yes, so good evening, everyone. So, Jerry, we are happy to have you among us for our first webinar. So, Jerry will be talking about Island Zero, and the Island Zero project is making progress actually. And it goes back to the 1970s, where Gerard O'Neill developed plans for large space habitat. One that could house 10,000 people was a level of design known as Island 1. This would be different from anything launched previously, as it would rotate to produce simulated gravity. And then we saw that designs for space habitat have always assumed that they would operate under 1G, but do we actually need the 1G? What about the zero point 0.9 or zero point 0.8 or less? So we'd need a much smaller structure in this case, first of all, and to carry out all the required medical research. This would also demonstrate the viability of some of the ideas behind space habitation, and later versions would house the personnel that will assemble the main structures. This initial unit is designated as Island Zero. Here is an opportunity to hear about this new development straight from the designer, Jerry, the most practical 1G space station concept I have seen. Jerry, you have the floor.
Thank you very much. So I'll share my screen and okay, so let me just take that away. So I'm Jerry Stone. I'm a freelance space presenter and I run Spaceflight UK. I've been giving presentations on astronomy and space exploration across the UK and abroad for over 55 years, starting when I was 14 years old back in 1969. So as you can see in this photo, I have a Blue Peter badge, earned from the world's longest running children's TV program. And this was from when I was interviewed for Blue Peter about how rockets work. So for tonight's story, we start by going back to 1969 and Gerard K. O'Neill, who was Professor of Physics at Princeton University. At the start of the new semester in the autumn of 1969, he gave an extra seminar to a few of his new students, in which he posed what was meant to be the first of a series of questions that would be investigated by them to increase their interest in physics. O'Neill later said, "As it turned out, once a first problem was chosen for discussion, it so occupied us that we never had time for a second." And working out its ramifications would occupy O'Neill for the rest of his life. The question he asked was, is a planetary surface the right place for an expanding technological civilization? Well, the answer seemed obvious. It would, obviously be on either the Earth or on the Moon or perhaps Mars. But the students went off and did their research anyway. And the answer they came back with was no. The main reason was that any planetary surface loses the sun for 50% of the time, which you cannot then turn into electricity. An alternative source would be needed. On Mars, a day lasts just about half an hour longer than on Earth. though you still need to provide power during the night. But on the moon, the night lasts for 2 Earth weeks, and you need a major source of power during that period. An additional problem for a permanent settlement is that on the moon the gravity is only 1/6 of that on Earth, and on Mars it's 1/3. So over a long time they will both result in major medical issues with the human body, especially with raising babies. So where should a structure be built if it won't be on a planetary surface? To answer that, we need to go back 250 years. So if this is the Earth, and here's the moon and its orbit, calculating that orbit would be a straightforward issue. But if we add just one more object, then the calculations become incredibly complex. And this became known as the three-body problem. And mathematicians worked for ages to come up with an answer. A series of answers was worked out in 1772 by Joseph Lagrange, so they're known as Lagrange points. L1 is between the Earth and the Moon, and L2 is on the opposite side of the Moon, and it's an excellent place for looking out into deep space. So this is where the James Webb Space Telescope is positioned. There's also L3 on the other side of the Moon's orbit, but frankly not a lot of use. But these three locations are unstable. Move away from them and you'll keep going. So space probes at these points need fuel to keep them in position. However, L4 and L5, 60 degrees in front and 60 degrees behind the Moon, are stable. Or rather, a large orbit around either of these points is stable. Move away and the combined gravity will pull you back. So back in the 1970s, plans were produced for designs of large-scale space habitats that could be constructed at the L4 or L5 points. They included one over on the left that I thought looked like a 1950s lampshade, but the best shapes were a sphere, a torus, and a cylinder. So these are not to scale, just to show the different shapes. O'Neill's first paper on the subject was published in 1974 and was followed in 1977 by his highly praised book, The High Frontier. I personally met O'Neill in 1977 when he came to Britain and gave a presentation at the British Interplanetary Society. Afterwards, I was part of a small group that took him for a meal and discussed his work in more detail. And I'm very pleased to say that I still have my copy of The High Frontier, which he signed for me. The plans were given designations based on their population rather than their shape. The first was Island 1, which would have 10,000 people. For comparison, that's about the size of these Italian towns. The habitat is the sphere in the centre, 460 meters in diameter. The rings in front and behind are where the agriculture takes place, and the engineering and processing facilities are at each end, including radiators to get rid of waste heat. The solar power panels required for production of electrical power are not shown. The mirrors that you can see reflect sunlight forwards and backwards to secondary ring mirrors and then through large ring windows to the interior, where the inhabitants live and do most of the work. Looking through one of the big ring windows, we can see that it's an inside-out world. There'd be houses, workplaces, schools, hospitals, sports centres and other leisure facilities, public transport, everything required for a town of 10,000 people. As you can see, we would take and grow earth trees and plants, including roses, but no aphids there, and other flowers, but not stinging nettles or dandelions. We'd also take bees to pollinate the plants and make honey, but we could leave wasps behind so we can have our barbecues in safety. Now, having said that, there may actually be reasons why we would need to have certain types of wasps, but we definitely would not have mosquitoes, which still kill about 250,000 people each year. Also, there will be no tsetse flies, lice, fleas or ticks, tapeworms, termites, hornets or cockroaches, or even flies. And no rats, snakes or scorpions. The ecology is obviously an area that would need extremely careful study and consideration, and it will probably be the most complex part of the whole project. So as you can see, agriculture doesn't take place within the main habitat area, but in the adjoining rings. It would be possible not just to have several crops growing in adjacent areas, but the same crop can be grown at multiple stages. This is because, unlike on Earth, where usually a given crop only reaches maturity and can therefore be reaped once a year, here there are no seasons overall. So we could have corn cropped 4 times a year, and with 2 sections, 50% out of phase, we could reap corn every 6.5 weeks. And with another 2 sections, that would mean new corn every 3 weeks. Similarly, we could have fresh strawberries all the year round. And by closing off a ring from its neighbours, we could have a different climate, perhaps hot enough for growing rice. Now, unlike this painting from 50 years ago, we wouldn't need cattle for beef. But we might well have dairy cows for milk, and also chickens for eggs and pools for fish. Following on from this design, NASA sponsored a symposium in 1975, which produced this ring design, also holding 10,000 people. The event was held at Stanford University, so it's known as a Stanford torus. The large mirror helps reflect sunlight off the central hub to the interior of the ring. A larger design was also produced at the next level to house 100,000 people. This was known as Island 2. We could make buildings from mooncrete, that is, lunar concrete. Though Scandinavian settlers might prefer to wait until enough trees have been grown in order to build their houses out of wood. Then there are the cylinders. These are the big ones, shown here as twin cylinders counter-rotating so there's no overall torque. Island 3 would be 4 miles in diameter, 20 miles long, offering a land area of 500 square miles, 3 times the area of Washington, D.C., and supporting millions of people. Agriculture would be carried out in the ring of cylinders at the front, so the same crop could be grown in separate cylinders at different parts of their growth cycle. Even larger version could be constructed with a land area of 20,000 square kilometres, that's 16,000 square miles, half the size of Switzerland. And as you can see, the cylinders have alternating areas of land called valleys and windows called solars. Sunshine would reflect off the main mirrors through the solars to the valleys on the opposite side of the cylinder. Unlike the smaller habitats, which would require sprinklers, these are large enough for natural clouds to form and rain to fall. At the ends, you could go mountain climbing with the additional benefit that as you go higher, the gravity reduces, making it easier to reach the summit. Gliding would be another sport, and close to the centre line, human-powered flight. Here's a view along one of the cylinders. With a mild climate and an environment without earthquakes, avalanches, tornadoes, landslides or tsunamis, life in space could be much more pleasant than in many places on Earth. You can get an idea of the scale from this view. But now let's go back to the other end of the scale with the Island 1 design. Rather than launch the building's material from the surface of the Earth, which would be incredibly expensive, it could be built from material mainly sourced from the Moon. Now we know what's there, thanks to the Apollo missions. Oxygen for the inhabitants to breathe. Silicon for windows and fiberglass. Metals, iron, aluminium, magnesium, plus titanium. Titanium content on Earth soils ranges from 0.1 to 0.5%, with a mean value of about 0.35%. Titanium in average Apollo 11 samples was 5.9%. And since Apollo, we know the Moon can also supply water, which also means hydrogen. The Moon offers two other big advantages. Firstly, there's no atmosphere. And secondly, we can use solar power. So combining those, we can build an electromagnetic launcher known as a mass driver to send the material out into space without needing rockets. And this would not need mining the Moon, just scraping the surface. To extract a structural mass of 500,000 tons would only need a volume 530 meters square by 5 meters deep. To do this, during 80% of the lunar day, would take under 18 lunar days, so it wouldn't even occupy a single bulldozer for very long. Though, of course, we need to extract material from other places on the Moon to obtain the different required material. Now, since these original studies, we now know that we'd also obtain special materials from asteroids. My calculations show that sending out just 125 material at a time, with just one load being sent every 10 seconds, it would only take 35 lunar days to send the entire mass. In fact, it wouldn't be quite as straightforward as this, as some work would be done on the Moon itself. On Earth, glass panels are made using float glass, with molten silicon on a layer of molten tin and then cooled and cut to produce flat glass panels. However, there isn't much tin on the moon or lead, which also has a low melting point, but there is aluminium, which melts at 660 degrees Celsius, which is under half the value for silicon. So the silicon would be separated, the glass produced, and the finished panels would be sent out. How long would a mass driver have to be? Well, as you can see, it wouldn't be a solid structure. There would be a series of accelerators spread out. And how much land it would cover would depend on the acceleration produced. So the first demonstration mass driver built by Gerard O'Neill and some of his students produced an acceleration of 35 g. So for lunar escape velocity, it would have to be just under 9 kilometers in length. Mass driver 2 produced 500 g, would only be a bit under 600 meters long. And mass driver 3 produced a staggering 1800 g and would only need to be 180 meters. However, 500 g would probably be better, as this would allow time to fine-tune the trajectory during the acceleration. If we come back to Island 1, O'Neill deliberately restricted the design in two ways. Firstly, by cost, which had to be no more than the equivalent of Project Apollo. This was so people wouldn't be able to say, well, it's a nice idea, but we can't afford trillions and billions and zillions of dollars. This would be at a cost that had already been spent. The other restriction was on technology, which had to be of what was available at the time. This was so that nobody could say, well, it's a nice idea, but it depends on this and this and this that we haven't invented yet. So the question was, we would still need some initial launching from Earth to set up the logistics for the whole scheme. And this service was intended to be provided by the Space Shuttle, which was originally expected to fly up to 50 times a year, dramatically reducing the cost of getting into orbit. In reality, the low flight rate and high cost of maintenance meant that this scenario wasn't possible. However, a few years ago, I thought that we've made many advances in technology since the 1970s. Improved materials, new alloys, new materials such as graphene and carbon nanotubes, improved processes such as 3D printing, and our capabilities in computing and robotics are many orders of magnitude beyond what we had back then. So I thought, if we were to start this now, we could do so more efficiently and relatively cheaper. So I made a proposal to the British Interplanetary Society and set up the Space Project, Study Project Advancing Colony Engineering. Now, I have to say that I prefer the term settlement rather than colony, but I needed that for the acronym. I started the project not by setting goals or saying what topics should be covered, but by asking the team members to come up with questions that would need to be answered in order to progress. And I put the first two questions to the team myself. All habitat designs assume that they will rotate to simulate 1G. But, I said, do we need 1G? How about 0.9, 0.8, or even less? There'd be less stress on the structure, meaning it wouldn't need as much material for its construction, so it would be cheaper to build. There would also be less stress on the inhabitants, on their cardiovascular system, their muscles, and their skeletal framework. They would be healthier, and over time they'd live longer, and they would also grow taller to a degree, and we'd have to take that into account in the architecture with higher doorways and ceilings. But an associated question is, of course, how much can gravity be reduced before it becomes a problem rather than a benefit? And the answer is not just nobody knows, but nobody has the slightest idea because it's never been done. But we will need the answer in order to finalise the designs for the large-scale habitats. I also pointed out that it is obvious that we wouldn't start by building an Island 1 habitat straight off. First, we'd need to extract the raw material from the moon and asteroids. Then we need to process these materials into the constituent minerals, and then manufacture the components that would be needed: girders, panels, windows, etc. And finally, we'd need facilities to carry out the assembly. And while all this goes on, and even while these facilities are being constructed, we need somewhere to house the workers who will be doing all this. So before looking at Island 1, 2 or 3, we went to the next step down the pyramid and came up with a concept which will answer both questions. And we designated this Island 0. This would be a relatively low-cost structure and could have many uses apart from building Island 1 and larger structures. So the aims of Island 0 should include being constructed from modular components, plus parts manufactured on site. This would be much cheaper than the ISS, where most of the sections that comprise it are completely different from the others. Also, we would have simulated gravity. The ISS does not have this because it's not designed to. It is intended as a weightless laboratory. But although workers out in space will be weightless, Island 0 would rotate, so inside they would be under simulated gravity, particularly important when sleeping, which would be the greatest portion of their day. And although we've had people in space for more than 50 years, this has never been done before. It should involve growing some of their food. And it should also involve development of demonstration manufacturing facilities to process material to construct examples of habitat components, and the option to do this in weightless conditions. So at the central hub of Island 0, weightlessness would be available. And this would allow the production of high-quality large crystals, for example, for electronics or medicinal use. Another possibility is the production of alloys using metals that won't mix under gravity, or even producing foam metal. So I've referred to these units as porter cabins in space. The basic question is, why have simulated gravity? And it would be easier just to have the unit operating under weightlessness. But the big problem is the detrimental effect on the human body. Without operating under gravity and having the body work against it, the following issues arise. The cardiovascular system has less to work against, and so the heart weakens. The heart changes its shape from an oval, like a water-filled balloon, to a round ball, like an air-filled balloon. Blood flow is no longer pulled to the lower part of the body. As a result, the lack of gravity causes fluid shifting to the upper parts. For example, astronauts' faces swell. Fluid shifts also affect the brain, the eyes, and other neurological functions. Muscles no longer have something to push against, and consequently they weaken. The skeletal structure itself also weakens from not having to push the body upwards against the ground. And this results in effective osteoporosis, which is a major study on the ISS. Recent studies by a NASA biologist suggest that spaceflight even compromises the immune system. It's because of this that everyone on the ISS has to carry out 2 hours of exercise every single day. Despite this, they are still relatively weak when they return to Earth. Some astronauts experience difficulty or even inability to stand as a result of lightheadedness or fainting. The exercise equipment has a mass of almost 2 tons, and so would have cost almost $100 million to launch on the Space Shuttle. With Island Zero, it will not be necessary to launch this equipment, or for everyone to have to spend 2 hours every day using it, so they can spend their time doing more useful activities. The base units of an Island Zero would be cylinders, 15 meters long with a diameter of 4.8 meters. They will be inflatable, like those developed by Bigelow Aerospace. To show the feasibility of this, when expanded, Bigelow's proposed B330 module was planned to be 16.9 meters by 6.7, considerably larger in volume than what I've proposed. Sierra Space is also working and testing inflatable units, as are Vast and Max Space, whose founder, Maxime de Jong, built Genesis 1 and 2 for Bigelow Aerospace, which were placed in orbit. The size was chosen to fit into the payload bay of Skylon, a fully reusable launcher that would take off and land on a runway being developed in the UK. The revolutionary-based Sabre engines would function both as a jet and later as a rocket. When operational, Skylon would be the long-dreamt-of single stage-to-orbit launcher, and launch costs would be brought down even lower than those offered by SpaceX. So the Skylon payload will accommodate a 4.8 meter diameter unit, but it's only 11.4 meters long. But that doesn't matter if a 15 meter unit can be compressed to 2.85 meters. Then 4 could theoretically be accommodated in the bay. However, they would have a total mass beyond Skylon's capability, but they would fit inside a Falcon Heavy payload bay, which does have the capability to carry 4 at once into orbit. So the original proposal assumed a ring of inflatable modules 5 meters in diameter rather than the 4.8, and making a circle like this, which would have a radius of 22.5 meters. But then I did some calculations on the simulated gravity produced by rotating a structure. And with a radius of 25 meters, even 3 RPM would only give 1/3 of the gravity. In order to have a reasonable rate of just 2 RPM, then in order to have 1 G, you would need a radius of 225 meters. To have a ring just slightly smaller than that, at 200 meters, would require a total of 84 units, and so it would obviously not be a low-cost structure. So how could we keep the number of modules down? Well, I decided that instead of being connected like this, if they were turned 90 degrees to be radially from the center, we could extend the tethers to 200 meters and give us 1 G. With an outer connecting ring, which would improve stability, then that would give us a view like this. The central hub would be comprised of other main modules at 90 degrees to the field of view. So inside, the modules would have various floors, and instead of ladders to climb from one to the other, there would be a spiral staircase fitted to the inside of the outer wall. So volume of one of these units would be 270 cubic meters. With 8 units, that gives 2100. Compared with Destiny, the largest module on the ISS, as you can see, each of them are considerably larger. And compared to the total habitable volume of the ISS, just over 1,000 meters cubed, Island 0 would have nearly twice the volume. So this is a scaled diagram. So in addition, we would need access tubes to go from the central hub to the outer modules. So if they were straight, then people and equipment could be falling at 0.9 G at the outer level. And this might be acceptable, perhaps using ropes and pulleys when transporting equipment. However, they would probably hit the walls due to the Coriolis effect. And I thought it would be impractical and expensive to install lifts. So as an alternative, we would have a series of access tubes approaching a curve. So a spiral option means people would transition to walking feet down when they reach the end of the tube. And we'd have 3 other sets. If you think that this isn't practical, I can tell you it isn't a new idea. In fact, it's almost 100 years old. I discovered that this had originally been proposed by Hermann Nordnung in 1928. Now, I'll come back to the idea of lifts later, but meanwhile, with some solar panels to provide power, here is Island Zero. Animation was produced by Adam Manning, one of the project's members. But I later decided it would be better if the main modules were horizontal rather than vertical. This would make much more efficient use of the floor area. And with the access tubes, it would look like this. They would connect to the upper floor, the outer ring to the lower floor. Increasing the rotation from 2 RPM to 3 RPM would mean that 1G could be achieved with a radius of just 100 meters rather than 200. So we change from this to this. And being smaller, we'd only need 2 access tubes. So here's a view from the side showing the central hub with solar panels and radiators to remove waste heat. Craft coming up from the Earth would dock at the ends of the central hub, and as only the central unit itself would rotate with the rest of the structure, the other 4 would counter-rotate so as to keep the solar panels facing the sun. It will also mean that approaching spacecraft would not have to rotate in order to dock. Further studies have shown that a rotation rate of 2 RPM is not necessarily required to achieve 1G at a rate that crew members can tolerate. In fact, studies suggested there is confidence that space settlements can rotate up to 4 RPM. So this translates to a system size of around 50 meters radius, and another possibility is even up to 6 RPM, which brings it down to 25 meters radius, which is like our original ring of modules. However, although these rates have been verified by Tom Morotta and Al Globus in The High Frontier, An Easier Way, I believe that with such a small radius, the gravity gradient between the head and the feet will make it uncomfortable. So I've stuck with 3 RPM, and here I've reduced the size of the solar panels in view of the improved versions that are currently in use on the ISS, which are less than 50% the size of the original ones. Now we could also add further main modules. So if the ones out at 100 meters were providing 1G, adding others closer in could provide 0.9, 0.8, and even 0.7. So the first additional module would be here at 90 meters, and we need one on the other side to balance the mass. Then we'd have modules at 80 meters and at 70. With this arrangement, we could carry out the research at different gravity levels simultaneously, which has never been proposed on any other design. In fact, Gerard O'Neill himself made it clear that experimentation for figuring out the right and best gravity for long-term human and animal and plant physiology was critical to long-term in-space living. Now, the other 6 modules that wouldn't be needed for this could be leased out to universities and research organizations to do additional studies, or to organizations to carry out commercial activities, and also construction prior to doing this on a large scale. There's also the possibility of using one or more modules as a space habitat, which would generate additional income. So all in all, the Island Zero concept offers a lot of opportunities. There's one other adjustment to the design. Let's look at the access tubes. I originally said that installing lifts would be expensive, but recently I came up with a new idea, and this is for a simple lift. Instead of an enclosed cabin on cables, it would just be a platform moved on a rack and pinion. So the structure would look like this. And this vertical option could deliver people and equipment from the central hub to all of the outer modules and to the upper or lower levels, like this. Once they get to the central hub, by reversing their orientation, people could continue to the opposite side of the structure. So they could visit all modules as well as the central hub. And I'd recently used a design application to show a possible model made with Lego. There's another possibility for Island Zero. That a small version starting at 4 RPM could also be used to take crews to Mars, supporting settlement of the Red Planet. We could adjust the rate of rotation during the journey so that when approaching Mars, it will orbit at 1.25 RPM and provide an equivalent of Mars gravity, 1/3 of Earth gravity. So the crew will be acclimatized to that gravity level when they arrive. Otherwise, they would spend about 7 to 9 months under weightlessness and then have 1/3 gravity on arrival. And NASA suggested that they may take 3 days to acclimatize before being able to go outside, which is basically a waste of time. On the way back, the spin rate could be slowly increased so that the crew was reacclimatized to Earth gravity by the time they returned. Of course, we need additional radiation shielding, being outside the Earth's electromagnetic field, but one advantage of inflatable modules is they actually provide better shielding than if they were made of metal. So what else could the space habitats be used for? If we remember the opening section that was about the potential lack of resources, which as we've seen is not a problem, and also about energy, well, using the plentiful silicon from the moon and germanium from suitable asteroids such as Psyche, people on an island 1 could build large solar power stations that could convert sunlight and beam the energy down to Earth using microwaves. This would be received at large antenna known as rectenna, and the beam would be spread out so that at ground level it would cover an area with a radius of over 5 kilometers and be collected by screens that would gather the microwave energy but not block light. And being spread out, the energy directly in the beam would only be half that of sunlight. So birds could fly through the beam without being affected, and animals could graze on the ground. The microwaves would be converted to electricity which would be fed into the grid, providing 10 million kilowatts at each site. In January last year, NASA issued a major new report on solar power. Over 90 pages long, it provides data on 2 reference designs which would be standalone projects. That is, they could be implemented without building large-scale space habitats. But although in this plan they would be constructed in multiple sections on Earth and then launched into orbit, a unit such as Island 0 would still be of huge benefit in housing the assembly crews. And although they would work outside in weightless, for the rest of their time, particularly sleeping, they would be under simulated gravity and not having to waste 2 hours every day doing exercises. In addition, NASA is also promoting commercial activities in low Earth orbit, and again Island 0 would be of use in this respect, as microgravity work, i.e. weightlessness, could be carried out in the central hub, whilst allowing the crew to spend their other time off duty and sleeping under simulated gravity. So Island 0 can achieve a lot. Back in 1974, in his first article on space habitats, Gerard O'Neill wrote, "It is important to realize the enormous power of the space colonization technique. If we begin to use it soon enough, and if we employ it wisely, at least 5 of the most serious problems now facing the world can be solved without recourse to regression." We could bring every human being up to a living standard now enjoyed only by the most fortunate, with high quality living space when the world population is doubling every 35 years. We would move much of our manufacturing technology off the surface of the Earth, using materials sourced from the moon and asteroids, rather than mining the Earth and using up our resources here. The effect of this would be to protect the Earth's biosphere from damage caused by transportation and industrial pollution. It would also prevent overload of the Earth's heat balance. And he said this 30 years before we started worrying about global warming. Also, we would have clean, practical energy sources. Also, as the resources available from the moon and asteroids far outweigh those on the Earth, and the living space gained from the construction of large habitats can outstrip the global population increase, it means firstly that we will never run out of room, and as a result there will be no need for any nation to attempt to claim resources from others. In other words, the threat of warfare would be reduced. That means moving into space will reduce war on Earth. And really, if there is any reason for going into space, this has to be it. This was effectively summarized in a quote from Frank White, who wrote The Overview Effect, about the effect of many people who had been in space on their view of looking back at Earth. He said, war and space exploration may be mutually exclusive, because if one occurs on a massive scale, the other probably will not. And it works both ways, and obviously we know which option we would prefer to see. And the development of Island Zero may well be the best way of moving forward in this activity. As for Island Zero itself, it can be constructed using technologies that exists right now. It can be launched using current boosters. It will rotate to provide simulated gravity unlike anything ever launched before. It will be able to operate at different gravity levels simultaneously. And there is no other structure designed that will do this. As a result, it can be used to provide essential medical research. It can house crews involved in commercial activities, including space tourism, and acclimatized crews going to Mars and returning to Earth. Obviously, more work is needed to finalize the design, layout, and construction options. A major factor is that this is not a proposal for a new type of satellite or space telescope. A structure like this has simply never been built before and will result in people living in working conditions never experienced prior to this. So I'm therefore putting together a proposal for perhaps NASA or the European Space Agency to carry out a Phase A feasibility study to verify the concept of Island Zero and produce a detailed design, including the interior. Meanwhile, I've applied to the Royal Astronomical Society for one of their small-scale grants to fund a 10-day study to investigate the design. Unfortunately, they won't be announcing the results of applications until November, so I've got to time to wait. If anyone would like to help with any of this, or if you know of any appropriate contacts, please let me know. Meanwhile, I've been in contact with Curare, an American company that manufactures Vectran fiber. This is stronger than Kevlar and 5 times stronger than steel. They supply it to other companies who use it to manufacture webbing. It's used as a layer in the construction of inflatable space habitat modules. In our correspondence, their manager of international marketing described Island 0 as the most efficient 1G space habitat I have ever seen. So we have a title and a logo. And bearing in mind that mankind's expansion into space could help solve many of its major problems, including a reduction of war, it seems appropriate to slightly amend the logo. And we also have a slogan, courtesy of Blade Runner.
In the off-world colonies, the chance to begin again in a golden land of
So I have
and adventure.
a summary file on Island 0, which I've recently updated. So it's now 5 pages. And my email address is coming up soon. If you'd like a copy, then please contact me. Or if you know anyone who'd like to arrange a presentation. So thank you very much. I hope you found this interesting.
Thank you so much, Jerry. Beautiful, beautiful presentation. Very, very interesting.
Thank you.
We are talking about Island 0 since some years, but this time you have really put together some very interesting innovation and design. And yes, thank you. Thank you so much. I hope that now this project will really take off. And
I hope so. I mean, the first thing is if the Royal Astronomical Society approves my grant, which is for 4,500 people, that'll pay for a study to be carried out by independent people looking at different aspects of the design. And that would be an excellent document to go into a full phase A feasibility study.
excellent. This is very good news. Oh, I see that a lot of people wrote something in our chat.
Good.
Maria, maybe we can try to give some of these questions.
Yes, I'm trying to go through the chat to see if there was a question or they were just talking. Okay. Maybe this is a question.
Made a kind of discussion, I think.
Yeah, I think they were just discussing with each other and stuff. Yeah, because they were replying to each other actually. But it's interesting, actually. Whatever you said, make them open more ideas. it's clear about climate and yeah, the airlock. Yeah.
Yes, each of the modules would have an airlock where it's connected to the outer ring. So if there is any problem at all, then it's not as though the whole structure will fail.
Yeah. Okay, so I found someone was asking something. I mean, someone else answered them, but it would be maybe interesting to ask you the question directly. So this person was saying using inflatables leads to the problem how to design the interior furniture, staircases, etc. Should these components also be inflatable, or should we prefer rigid structures, including all furniture?
So I would certainly say that in the main modules, the heating floor can be part of the inflatable structure. Possibly some other sections might be able to be included. I've sent inquiries to Sierra Space and Vast and others, and they don't seem to be interested in answering their email. So I don't know yet, but otherwise they'd be taken up and added after implementation.
Yeah. Okay.
So in the main modules, the upper floor would be the living quarters, which would probably not have windows because as the whole unit is orbiting the Earth, it'll be in daylight for just over 45 minutes and then in darkness, and that will alternate 16 times during a day. So if there are no windows in the upper section, then they can get proper sleep without any sunlight coming in. But there probably will be windows in the lower section. They can look out to Earth, and it's possible that equipment and experiments they're doing might need that.
Okay. I think the answer clears everything, makes it more clear. I'm trying to see. Oh, another question. How to move between peripheral modules in Island 0?
Sorry, how to move between
peripheral modules?
Oh, the outer, in the outer
Yeah,
ring.
I think this is what they mean by the question. Yeah.
That outer ring will be 2.4 meters in diameter, so you can simply walk along it.
Walk. Yeah.
Okay, so I hope the person is still connected and heard the answer. Well, that's everything in the chat. That's everything for the questions. Yeah.
No, I would like to say something. It's a detail, but I think it's interesting. In these days, I had conversation with some astronomers. They participated to a side event at the United Nations General Assembly Friday. And there were several astronomers talking, many of them from Africa and from other countries. And there was a shared concern about the dark and quiet sky because of the number of satellites that are quickly increasing in Earth orbit.
Yes.
And they are very concerned because this high number of satellites is disturbing the observation of the sky and of the stars and so on. So during a conversation I had with a couple of them today, I suggested that expanding into outer space would be also a solution for this problem, because the high number of satellites that we have in orbit is another confirmation that we are making, let me say, too many things on the Earth surface, and so we are increasing the pressure on in our closest world, and filling the orbit of satellites. It is useful for global communication, but it's very, very bad for a number of things, including astronomy, and including the fact that when even the small new generation satellite that will re-enter, that they are designed to re-enter the atmosphere at the end of their operative life, re-entering the atmosphere, they will burn and they will release gases, vapors in the atmosphere that are noxious, because they are vapor of metals and of other materials, plastic and so on. So it's not, it should not be considered a definitive solution to make satellites re-enter the atmosphere and burning. But very much better is to collect them, bring them to repositories, orbital repositories, or the Lagrange points, and then rework and reprocess these materials. But however, the general consideration that we can make from a philosophical and anthropological point of view is that we are crazily increasing the volume of things that we are doing on Earth and our global communication and so on. It is like if we only think that we can live here and we cannot expand. But if we start thinking about expanding, and then we have to think about simulated gravity. So the Jerry project is fundamental for this thing. And I hope that finally, and with our Congress, I also would like to remind that these webinars that we are doing, this one is the first one. No, well, we made the SRIC4 number zero webinar 1 or 2 weeks ago, when we introduced the Congress and presented the Congress and so on. However, these webinars that we are making are discussing the key points that we will discuss in our Congress. And I invite everybody to visit the dedicated website that is 2026.spaceonessence.space, and where you can see our call for papers. You can submit your papers, and you can also already register to the Congress. So we are still distant about 10 months, because it will be end of June next year, end of June. But we think that a good preparation of the Congress is very important, because our Congresses are not simply let me say, giving a floor to very good speakers, but we want to understand something during our Congress. We want to understand the status of civilization and what is to be done. And we have the presumption to give a final resolution indicating the priorities for the next 5 years, 2000 toward 2030-31. We will have many webinars, at least 16 webinars, 2 per month, but even more, because we have many speakers, many valued experts that are interested to talk. And so we want to give them 1 hour time to describe their concepts, because of course, in the Congress, we can present papers of 10 or 12 pages each one, but the presentation time will be more limited. It will be only 10 minutes or 12 minutes maximum. Therefore, with our lectures of 1 hour, we want to give our participants, our speakers, time enough to describe their concepts and to give all, as Jerry has done today with his very interesting and informative lecture. So yeah, let's see if we have some other think. Do they need to do EVA to go between modules? No, no. I think
Yeah.
I can anticipate the answer by Jerry, because there are connection tubes, so you can simply walk.
Yeah, right. As I said, some of the modules could be used for space tourism. And if those people want to experience weightless, they can just go to the central hub, and from there they could even do an EVA, go outside if they want to. I don't see anything against that. So it provides a lot of opportunity.
Yeah. Good. Alexander Mikhailov says, so those connection tubes large enough to walk inside should also be launched. Well,
that they are also inflatable units.
They're inflatable, but
compressed and then expanded out to the tube, either the straight ones or round for the outer ring.
But they should have a protection shield too, because of course
They will have. And as I said, units like this provide better radiation shielding than metal units.
Yeah. So maybe the inflatable mattress will be big enough and thick enough, and maybe some polymers inside and some materials that can prevent
so with
radiation.
Bigelow's planned B330 module, that had walls just under 1/2 meter thick.
Okay.
I've assumed the same size in all of my modules. In the main modules around the outside, the central core, and the outer ring.
Great. So everything will be inflatable and chemically rigidizable.
Yes.
Yeah,
stronger than steel.
Some years ago, I was working with ESA about inflatable structures, and yeah, there are several techniques to get the inflatable models rigidized. By the way, it's enough, even the few molecules of gas that remain inside the compressed module to expand, because when you are in the void, in the empty, those few molecules of gas remaining inside are enough to make the module to expand. Then when it will be expanded, then the sun will provide the necessary cure to make it rigidized. It is called sun cure. Sun cure. Okay.
Yeah.
And so many studies were made also in Europe about that, and unfortunately, none prototype has never flown so far.
Well, Bigelow did launch Genesis 1 and 2, which were unmanned.
But not I was talking about Europe.
Yeah, no, nothing from Europe yet.
No. But
Although
many
also
studies
produced the expandable module, which was attached to the ISS, and it was meant to be there for 6 months to a year, and it's coming up on its 10th anniversary. It's still there. The crews don't use it for working in, but they do go in periodically to test its rigidity and that it's kept its pressure, which it has done. And they also check radiation in it as well, which has never been a problem.
Okay. So we have another question saying is from Benjamin Bates. Will there be any architects speaking in this webinar series? I love this solution, but wonder how we might make these inflatable units feel like home. Yes, of course, we have one of the next speakers is Werner Grandl from Vienna, Austria. He is an architect and he is also a civil engineer. And he will be speaking of a particular application of a rotating structure that is an industrial application for making factories in a Lagrange point and or in orbit and so on. So he will take care. Werner will take care of architectural solutions for an industrial plant rotating with zero gravity in the hub and quarters for the for the crew in the rotating part. And yes, definitely. By the way, one of the concepts that we are very much focused on in our discussion about living in space is that living in space should be beautiful, should not only be ergonomics, should not only be safe, should not only be structurally appropriate and so on. It should also be beautiful. Because now we have to consider that Island Zero is a prototype, is a demonstration project. So we only want to push to start experimenting simulated gravity because we have an enormous delay on this point because we are experimenting since 60 years with zero gravity, but nobody so far thought about making something concrete experimenting simulated gravity. So this is our goal, proposing Island Zero. But when we talk about settlements, when we talk about big habitats on the O'Neill model, then we want to take care of having beautiful environments inside. We want to take care about having gardens, about having ergonomicity and all what it make life a pleasant experience, and not to feel anymore like astronauts, because astronauts and explorers, they are military. They are there to have a mission and to go exploring and to make science and so on. So they tolerate for 5-6 months an environment that is like a laboratory. Think about the interior of the ISS is a scientific laboratory. You cannot have fun over there. But we have to think about an environment big enough that people can also stay alone if they like, and not only in their small quarter, but also in large environments inside the habitat, in woods, in fields, in gardens with flowers and forests and so on. So this is very important, and it was all already present in the Gerard O'Neill's design.
Yes.
Because he perfectly, he was focused on living in space, settling space, not only go there for exploration, but to live, to expand, to make people populate greater Earth, let me say, in principle, then also around Mars and the asteroid belts and so on. But however, yes, to think about beautiness is a main one of the main requirements for living in space.
Yeah. And this is something that large-scale space habitats have as a great advantage over communities on the moon or Mars. You cannot really make them look like Earth, but the islands 1, 2, and 3, as you saw, you would imagine that they were on Earth if it wasn't for the shape. And it will be living in space. When people talk to me and I ask about what kind of people will go into space, and I say, well, in the long term, it will be shopkeepers, teachers, office workers, doctors and nurses, builders, woodworkers, professional sports people, any type, practically any type of worker that you might find in a town on Earth.
Yeah.
There'll be some that we won't need up there, but all the others will be living, in their towns and villages, just as though they were on Earth.
There will be restaurants, of course.
Of course, yes. All the leisure activities and people to man them.
We want to eat a good pizza in space.
Yes.
Of course. Well, so, I see someone is still writing something. Mo with. I'm sorry if I don't read correctly your name. So I read what he wrote, but I'm not sure that I understand it. Sarcad effects equation. Sarcade is written Sarcade effects equation says that F50 is minor than F100. Sun attracts the Earth and the Earth attracts the Moon in terms of radiation. Radiation considers as a force of attraction in a direct or indirect way. This message is repeated twice. I don't understand what it means, so maybe Jerry, you do?
Radiation isn't a force attraction, it is only gravity. In Earth orbit, we are inside the Earth's magnetosphere, which deflects a lot of radiation. There is still some that comes through, obviously solar radiation, sunlight, but there is also cosmic radiation.
Yeah.
Out at the at the distance of the moon in L4 or L5, you're outside the Earth, 99.999% of the Earth's magnetic field, and so you do need additional shielding. It's been proposed that as well as structural mass, another possibility is simply water in polyurethane containers. And if you can have an inner wall in your structure which is purely made of water, that will give a lot of protection. Plus, of course, you could also use the water for all kinds of things and recycle it so it doesn't get used up.
I also heard another thing that I didn't imagine, that if you have a big enough environment, field of air, air will also protect from radiations. If you have a big construction like Island 3, for instance,
Yes,
field
yes. It
air
would have to be really
will
big.
also be a protection from the radiations. I heard that thing, and it is strange, but maybe not that strange, because we know that even the atmosphere on Earth is protecting us from radiation.
And most of that is within the first, say, 10 miles.
Yeah. Okay. So, well, okay. Werner is thanking you, Jerry. Very well done. Yes. So I think that maybe we can conclude this very, very interesting and productive webinar. Maria, you're still with us, so maybe we can
Yes, I'm here.
and okay.
Yeah, so I think we reached the end of the webinar, answering all the questions, and it was a really interesting topic, the habitat. Thank you, Jerry, for your intervention, and we look forward to having you in the virtual also Congress soon, next year. So, yeah.
What is the next one? So the next one
is on next. It will be Tuesday next week.
Yeah, next week, the 7th of October.
The 7th, yeah.
We have Bill Diamond, that is the president of the Search for Extraterrestrial Intelligence. He will give a lecture on a search for life beyond Earth, how it works, where it stands, and why it matters. And then the 13th of October, we will have the second webinar of the preliminary webinar of the Congress, that will be Werner Grandel with the Lagrange factory and geolunar space industrialization. So these are the next dates, only 1 week distant each other, but then we will have a little bit more distance, at least 2 weeks. But it will not be the only time that we will have one webinar per week, because we, as I said, we have many topics to arguments to develop. Yeah. Okay, so thank you very much, Jerry. Thank you, Maria, for your beautiful conduction, and
my pleasure.
See us.
Thank you, everyone.
Good evening, everyone.
Thank you for your comments and questions.